Exponential and logarithmic models, there's actually more than just exponential and logarithmic models. So first of all, we already kind of talked about some exponential models, but so exponential, they go through kind of 5 different types of things you could have with exponentials, and logarithmic models, there's probably more. But an exponential, the general form is y equals a e to the bx, okay? Where b is usually like the multiplier or the rate of change or something like that. And a is usually what? You guys know what a is usually? This is usually the initial value, because if you plug in 0 in here, okay, you end up getting, so at time 0 or when something is equal to 0, this number you end up getting y equals a. So this is usually your initial value, and this b is usually your rate of change, and that might be an interest rate or a decay rate or something like that. And for the most part, exponential functions, you kind of know what they look like, right? They kind of start like this and they go up. Or they can start up here and go down slowly, or they can start from here. And what else can they do? I guess they could start like this way if it's a negative exponential, and then go down really fast and stuff like that. Or it could come from the other way, like this. So all of those would be kind of models of exponential functions. And this is kind of an exponential growth. If it's exponential decay as in like a what do you call it, half-life problem, or you want to find out how much your computer will be worth 20 years from now, okay, then you could use a decay model, and that's just y equals e to the negative bx, okay, where whatever the rate of change is, it's going down by that amount, okay, so multiplying by a negative percent each time. Anyway, so that's a decay model. And then they have something called Gaussian. I don't think we're going to have a homework problem. And but it is an exponential model, and it's how you get your bell curves and stuff. A equals e. They would probably, if you took stats or something like this, they would probably talk more about the Gaussian model. And I think Mr. Beamer and I decided we're really not going to stress it very much. But it looks like negative x minus b squared divided by a constant. And Gaussian models look like bell curves. So something like, doesn't go back up, it kind of goes left. You know about bell curves, right? That's how they do standard deviations and all that kind of stuff. And so we're not really going to talk about that form too much, because it's, I don't know. Anyway, and then we have something called a logistic model. Logistic. And these come up a lot in real life. And they have the form y equals a over 1 plus be raised to the negative rx, okay? And logistic growth models are they're like more realistic models of populations or bacteria or lots of different things, or like they come up in business, and they look kind of like this. They start off with an asymptote down here, and then they start increasing exponentially, and then they kind of start approaching another asymptote that way. So this might be like you, I don't know, you start a company, and at first your profits start going up really, really fast, but then you kind of reach this saturation point. So that might be like something like Starbucks or something, you know, like at first they're growing like super, super fast, but when you start reaching that saturation point. When you have a Starbucks at every corner, they're still going up, but not going up as fast. So there's kind of a point. And a lot of businesses base their models on that, and when they can find this point, that's really important. Also, like bacteria or populations, right? Population growth, like back in the 80s when I was in college, Louisville just had like 10,000 people in it, Louisville Superior, and there's like no one here. We used to ride our bikes. This was all like fields and stuff, you know. And then all of a sudden, like in the late 80s and the 90s, super fast. But now, we're still kind of growing, but growing a lot slower because, you know, they don't want to, you know, have Manhattan in the middle of Louisville, you know, so there's restrictions, you know. But like I told people when I was in college, you know, with Superior and all that, we used to ride our bikes out there, and there was nothing. It was just farms, and we used to ride, the only Louisville was downtown Louisville, and that was it. Just there wasn't any of McCaslin Boulevard. It was just like fields and stuff like that. How about that? Anyway, I'm that old. Anyway, older actually. So anyway, that's a logistic growth model, and usually this is kind of called the limiting value. Limiting value. That's not limiting value, which is, and that's kind of like your asymptote up this way. So if it's approaching, so say the maximum population of this area is 100,000 or something, that would be the limiting value. And this again is your rate of change. I think B, I'm not exactly sure, but I think this would be where you start at, okay, and this would be your rate of change. But we'll do a couple problems with that. And then, so that's logistic growth models. And then we have logarithmic models. Logarithmic models, which kind of look like, you know what those look like already. They kind of take the form, in general, a little more general. Then we've had y equals a plus b ln x, or y equals a plus b log a plus b, that says b log x, not log x. And for the most part, those look, you know, kind of like that. And we've seen some logarithmic models, like with the little earthquake activity. You've done things that go up kind of fast, and then, but they have an asymptote over here somewhere, okay? And that asymptote, is the asymptote A? X equals A? I'm not sure. We'll talk about it more. And then, but they go up kind of fast, and they keep going up, but not as fast. And those are things like the Richter scale, or decibels, which I assigned a problem like that on your homework. All right. So anyway, let's look at some of the problems that you will be doing. Let's see if I can find it. Dropbox folder, Miss Cox, Pre-Calc Advanced. I'm looking for Pre-Calc Advanced 13. There we are. Chapter 3. I think I copied this as a PDF somewhere. The same thing that you have. PDF. You see that? Log way, going course. Uh-oh. 3-5. Oh, here. Oh, it's a Word. Is that a Word file? I guess it must be. All right. So I'm just going to write right on top of this. So for the first one, if you saw a problem like this, and most of these you can solve, whoops, where'd that go? You could solve using a graphing calculator, but I don't really want you to, I want you to know how to solve them abstractly, even though at the end you're going to have to use a graphing calculator anyway. But like if you took a test or something, I'd want to see the algebraic work where you plug in log, log of something at the end. But you could always solve these graphically as well. So, so here's an exponential, the population y in millions of a large city can be modeled by 1.8 e to the 0.26, where x equals 0 corresponds to 1990. In what year did the population of this city equal 2.5 million? So all you have to do is plug in 2.5 over here, right? And then 1.8 e raised to the 0.026 x, and then you just have to solve that for x. So to solve that for x, what would I do first?
Divide by.
Very good. You divide by 1.8. So 2.5 divided by 1.8 equals e raised to the 0.026x. Then how do I get rid of that e there? You can take the natural log of both sides, because the natural log and e cancel each other out. So if I ln both sides, ln, I get that 0.026x equals natural log of 2.5 divided by 1.8. And then I would just divide both sides by 0.26. And again, it's kind of better to solve for x first and then plug everything into your calculator. And so if you did that, you get the answer to be about 12.6 years. 12.6 years. So that would be, what's that? The population of a large city can be modeled by this corresponds to 1990. What year did it reach 2.5 million? So I guess the growth rate must be 2.6%. Oh, because it started with 1.8, right? Because if I plug in 0, you would have 1.8 million.
That's just what year though?
What year? Oh, and what year? So 12.6 years from 1990 would be 2002. That's what the cheater book said. That's not right?
No, it is. I did.
Yes, Marcus.
Shouldn't you divide by 0.026, not by just?
Yeah, sorry. Yeah, I did when I did it. Yeah, sorry.
Okay.
Sorry about that. Thank you. Okay, you're good on that one? All right. So the next one is tricky. I like the next one because it's kind of fun. So, you ready? Can I move on? So with the next one, what you want to do is, so it's still an exponential growth model, but in this case, they don't give you a specific equation. So what you have to do is come up with the equation. And this is kind of what we're doing with the cooling corpse lab on Monday, which is kind of fun. Figure out who killed the bad guy or something like that. Or killed the good guy, sorry. Someone the bad guy killed. So 2 hours after bacteria were introduced in culture, the population was 256. 5 hours after that, the population was 541. What will be the population 24 hours after the start of the experiment? Okay, so you start with y equals a e raised to the bx. And then you have to get two equations and two unknowns. All right? So it said 2 hours after the bacteria was introduced in the culture, population was 256. So you're going to set up one equation, 256. You don't know what A is, okay? And you don't know what E is, but you know B, and you know X in this case is 2. Okay? So there's one equation, and then you have another equation, 541 equals A e to the B times, 5.
7.
It's 2 hours.
Oh, thank you. Whoops, good thing. 7 hours, because it's 5 hours after that. So now you have to solve this. You have two equations and two unknowns. Anyone have any ideas how to do that?
You do 1 for X, or 1 for A, and 1 for N.
Yeah, you could solve one for A and plug it in the other. what I kind of want to do is, I think it's easier that the way I did it, I said that A equals 256 over e to the 2b, right? If I solve this equation for A, and over here I get A equals 541 over e to the 7b, right? Yes? And then since A has to be equal to A, which is probably your starting value, that's not 776, that's 7b. I set these two things equal to each other and solve for b. So I have 256 e to the 2b equals 541 e to the 7b. And then what I did, I cross multiply, well, what did I do? I cross divided. I said I divided both sides by 256 and I multiplied both sides by e to the 7b, because then I can have that e to the 7b divided by e to the 2b equals 541. I think this is kind of the easiest way to see. In the book they used to call them negative exponents and stuff, but I didn't like that. See what I did? Okay. I multiplied through by, the reason I wanted the 7b up here, I multiplied this by 7b over, I multiplied this side by 7b and this side by 7b, and I divided this side by 256 and this side by 256. That way, I get that e to the, what do I do with these exponents? Subtract. E to the 5b equals 541 over 256. Over 256, and then I can ln both sides, and that gives me that 5b equals ln of 541 over 256, and then I divide by 5, right? Divide both sides by 5, divide by 5, and I get b equals this. Now, you're not done yet, even close yet, okay? So what I would do then is get your graphing calculator, okay? And I would okay, so with the graphing calculator, I would, how do I do that? Always in front. What I would do second quick is clear. Take this value, natural log of 541 divided by 256.
Just let equals not first.
I think I could just divide because it's natural log of that over that, isn't it? You're gonna give me that? Let's see.
Yeah, you can.
Divided by 5, and I get this. Okay. Now I'm gonna store that. See the stow? Do you know about storing things? Go to stow. See stow down here? Go to the stow and get me some dough. Okay, there's the dough. There's the stow. So I'm gonna stow that. You stow that answer as alpha b. So you hit alpha and then b, and then it's gonna put that in there, so you don't have to worry about rounding off and stuff like that. Have you guys done this? Maybe. So now I know what b is. I still have to find a, right? So all I have to do to, find a is take one of these equations and plug it in. Okay, so I'm going to go 256 divided by. I think I'm going to put this in parentheses just to be safe. Second e raised to the 2, and then you hit recall, which is right above the stow key. So that's that second recall And then you're gonna go, oh, what did I
You
do?
just take an alpha B,
Sorry, I screwed
or
up.
you can take
Okay.
an alpha answer.
Can I go back?
Or
Really,
second answer.
really?
You can use
Sorry, I messed up. How do I get back
You just
there?
do one
Uh,
person.
clear.
clear,
Clear?
and
Clear?
then second enter.
Oh,
Ah!
You need to-
Let me try again. Okay. So, what did I do? 256 divided. Come on, you. 256 divided by E. I'm gonna go parentheses again. Second E to the 2 alpha B, right? Alpha B. Okay, and then I am going to close both sets of those parentheses. I'm going to store that. I could either hit enter and then store it. I could enter it, and then I'm going to stow that as second, or what did I do? Alpha A. Just alpha?
yeah.
Alpha A. There we go. So now I have A and B, okay? And I store them, and then I go back to my original question, and it says, what will be the population after the start of the 24 hours after the start of the experiment? So we're going to plug 24 in there, and I have A and I have B. So I'm going to go, so I'm going to get my calculator back, and I'm going to get A, so I'm going to go alpha A E raised to the alpha B times 24. Did I do that right? I think I did that right. Okay, and let's see if I get it right. 6,887. Did I do that right? I think I did that right. Okay, it seems like it's too, no, that's okay. Okay, yes? You're good? You get that? So the population would be 6,887 bacteria. Questions? Okay, that's a tricky. All right, so the next ones aren't too bad. That's the worst. That's the worst of it. So then the next one I have on this sheet, it deals with a radioactive isotope. I don't know if I need to take you through the entire thing. Do I? You might have one like this. Example 3. Radioactive isotope has a half-life of 1620 years. So what this means, the way you model this, again, it's an exponential growth problem. AE to the A to the BX. So it looks like this again. And then Y equals AE to the, you don't know what B is?
You know, A, five,
Yeah.
Wouldn't it be? Yeah,
It comes out to
negative?
be negative anyway. Okay. So you'll